All right, good morning, everyone. Welcome back to Math 154, Week 6, Lecture 1, February 16th, obviously. All right, so we already know that 2.3 is due on the 16th. 2.4 we will finish, as well as starting 3.1 today, but not finishing. So 2.4 will be due on the 23rd, a week from today. We know our current Excel file currency is due on the 21st. There will be a new discussion board discussed today. Then this is one that absolutely everyone must participate in. This is going to be due on the 23rd. This is from pages 102 and 103 of your workbook. We will talk about this in more detail during class as always, but the basic idea is the worksheet or the activity that's on the worksheet from pages 102 and 103. It only does something like ages 25, 30, and 35. But what we're going to do is just, if I had 5,000 students, we would just keep going through and going through and going through. So first 5 students will answer for age 25. Then the next 5 students would answer for 6 through 10. And actually, it's just they only give one age group, and I think it's 35. So student, it'll be questions 1, 2, 3, 4, and 5. So first student comes in, answers question 1. Second student answers question 2, third 3, fourth 4, fifth 5th. And those would all be based on the age 25. When student number 6 comes into the activity, they'll answer question 1 as an age of 30 based on the activity. Then student 7 comes in and answers question 2 with an age of 30. When student 11 comes in, they'll answer question 1 for an age of 35. When student 16 comes in, they'll answer question 1 for an age of 40. So this enables everyone to participate. This will be a double grade, and it will count as 2 zeros if you do not participate. I haven't had that many of these yet, so I wanted to make sure that we definitely did this one. And then finally, we will have a quiz. This is going to be in Canvas. Remember, all your quizzes do get put in Canvas. And this will be based on page 101 of your guided activities, your guided worksheets. It's going to be based off of question 4. The only thing you have to do is find the answers to A and B. There might be several other blanks in this table that you'll see on page 101 that we will look at later in class. And you only have to answer A and B. Make sure you round to the nearest whole number. If you round to the nearest 10th or 100th, it will be marked wrong. If you round incorrectly, it will be marked wrong. You don't want to get these wrong. So make sure you understand how to round. You don't want to do the problem basically right and then lose everything because of rounding. So again, don't fill out any of the extra blanks. You don't have to do any extra work to get these. It's just a, a basic proportion table. And yeah, you just need three corners and then a blank for the 4th corner. Do that cross multiplying and you can get your answers that way. So that quiz will also be due on the 23rd. So we got quite a few things due on the 23rd, but the discussion board should be super easy. Just go ahead and knock that out as soon as possible. Everything should be live in Canvas. My math lab, I think I still need to make the 2.4 homework due date in my math lab, but that's not a big deal. You still have access to it. The discussion board is up, the quiz is up. Besides that, we're going to pick up where we left off, talking about 2.4 before we eventually get into chapter 3.
All right, and you might, this might look a little different. I came back and kind of did this again, or I think this is just an old file and it's about the same stuff, a little more, a little less. Don't worry about any things that you see up here that you didn't see before. We're going to talk about that. So we talked about all the PE ratio stuff. We very lightly touched on what CPI is. And I wouldn't even say lightly, we decently touched on what CPI is. It's a number that gives us a way of comparing the cost of something one year versus the cost of something another year. And what a CPI is typically used for, the way that number works is it's considering all goods available to the whole world, not just a gallon of milk or a computer chip or an Apple Watch or something like that. When you talk about one specific item, they usually don't scale exactly to what we call inflation. They may go up a little more, they may go up a little less. But the CPI gives us a way to determine whether something was cheaper in the past relative to what the dollar was valued at then, or if it's cheaper now / in the future relative to what the dollar is worth now. So a gallon of milk was, let's not even do the milk because it's on the screen. Let's say a ream of paper costs $1 back in 1990, and it costs $1.50 in 2020. And And you could say, well, when was that ream of paper cheaper? And you might say, well, obviously it was cheaper in 1990 because it was $1. Well, no. When we say cheaper, we're also thinking relative to the value of the dollar. So yes, on an absolute level that really is not even anything we worry about, a ream of paper was cheaper in 1990 because it was $1 and it's $1.50 now. But again, we're thinking about the value of our dollar. The dollar was worth more in 1990. So it was a lot harder to get $1 to buy that ream of paper. But it wasn't like a lot harder, maybe 50% more difficult, maybe 100% more difficult. Just depends on how the inflation has happened over the last 30 years. And those CPI values give us a way of, again, accounting for that. So all items don't inflate equally, and that's what we're going to do some examples of coming up. For example, milk back in 2006 cost about $4 to $5 at the store for a gallon. And again, regular milk, not talking whole milk, not talking organic. Now in 2020, it's about $2 for the same, like $2.20, $2.30 if you're buying 2% milk. So that milk definitely did not inflate at all. In fact, it deflated because the dollar is weaker now after 14 years. It's gone down pretty much every year. Notice I said pretty much every year. It doesn't always go down. A computer back in 1995 cost $2,000, but now it costs about $250 if you just want to get a mediocre laptop that could still do a million things more than what that 1995 computer could do. So computer prices didn't inflate, and we were lightly talking about this last time. It was definitely much more expensive to buy a computer in 1995 because the dollar was stronger and it cost you more of them. So those dollars were harder to come by because they were valued more, and the sticker price is almost 10 times as much. So a weaker dollar means you're going to have more of them on hand, but that also means that the items generally, due to inflation, would be more. But these two items did not inflate. Then there are other things that inflate more than usual. Things that are typically, how do I want to say this? Fun things, they tend to inflate out of proportion. But fun things that aren't necessarily just technology. Like, let's say you wanted to go to Busch Gardens. That's a super fun thing that if you were to compare the cost of a day ticket back in 1995 versus in, let's say 2019, because who knows in 2020, right? Maybe they got 50% off all the time. Anyways, if you just did the day ticket, it was definitely going to be cheaper back in 1995, even with that stronger dollar. So inflation is different every year. Sometimes inflation is 2%, sometimes it's 1.5%, sometimes it's 3.9%. Sometimes it's negative, which means deflation, as we've very lightly talked about, happens occasionally. But due to us coming off of what we call the gold standard, a lot of people think that our dollar is backed by something. The theory now is that it isn't. It's backed by hopes and dreams. Up until it was the late 60s or the early 70s, somewhere in that ballpark. I don't have the data in front of me. But that was when we came off the gold standard, which meant back in the day, we used to have just a room full of gold, and if we wanted to print more money, we had to have more gold. That's the basic premise. So that gold was there just saying, all right, the dollar, if you wanted to just turn it in for a hunk of gold in I guess, Fort Knox or wherever, then you could in theory. Now they said, well, we don't want to just keep stacking gold in a room eventually, especially because eventually gold will run out. We will tap all of the gold in the earth eventually, as well as silver and any mineral like that. I'm not saying it's going to be in 5 or 10 years. It may be 100 or 1,000 years. That's not what we're here to debate. But because we came off of that standard, the dollar weakened extremely quickly. So we saw inflation, and again, inflation is what causes the dollar to weaken. I want you all to hold up, or at least imagine yourself holding up a $1 bill. And then inflation is you cutting off a small portion of that bill, and now it's only worth 98 cents or 98 or 97 cents. Or if you're talking in the 70s and the 80s when inflation was 10 to 15% every year, that means you're cutting off a dime to 15 cents of that dollar. So what you could buy, whatever you could get for $1 in, say, 1975, The next year, now that dollar is only worth 85 cents. You're not going to be able to buy the same thing anymore. Again, across all goods, not just one particular good. This past decade, and actually the past 2 decades, inflation's averaged around 2 to 3%. We have the Fed that regulates that and tries to maintain that. Currently, right now, I know that's what's the word? I was redundant there. Currently, right now, so currently, we're actually, or the Fed is trying to bump up inflation because of everything going on, but let's not get into the greater grand details of that. It's some interesting stuff that you can look up, and if you don't like reading articles, you can find someone on YouTube rambling about it. If you are going to go to YouTube, though, make sure it's not one of the crazy people that are just making things up on the fly. Have someone that's, citing sources. You can find another video of someone else saying about the same thing. Because for every good person on the internet spouting truths, there's the opposite person somewhere. All right, so getting to the actual point of this, how we're going to use it in examples, how you can use it in the example in the real world, because you can pull up these CPI values. They're just numbers in a table on the internet. And very often you can find them in an Excel file. And one of your homeworks, clearly you probably can guess, you'll be doing something like that. So to be able to compare the price of a good from 2 different years, you must convert them to the same year's price. So the same year's dollar. So kind of like a US dollar and a euro has a different value, the dollar in 1995 has a different value than the dollar in 2020. So converting from a dollar to a euro is literally the same thing as converting a 1995 dollar to a 2020 dollar. It's not the same conversion values, but it's the same concept. And you know what that concept is? It's proportions and ratios. So we'll be looking at tables, we'll be drawing or imaginarily drawing boxes around numbers, trying to get 3 numbers in a blank in those corners. And that's the whole process. That's what I love about this course. We get to talk about a wide array of topics, but be able to keep bringing back the same simple mathematical idea and using it in a wide way, in a wide array, wide way, whatever. All right. Hint, in a CPI table, read across the row to compare the prices. So the row is usually the year, so that's you converting to the same dollar. So we will see this right now. So in a CPI table, in order to compare, you need a completed row. So you need to be able to see, all right, in a 2005 dollar, which thing is the lowest? That would be the cheapest. Or in a 1990 dollar, which thing would be the cheapest? And it doesn't actually matter which currency you convert to. One student could choose to convert everything to a 1995 dollar. Another student might choose to convert everything to a 2020 dollar. Because this idea of proportionality holds true. Remember, that's the way we're solving things. That means if it's cheaper in one currency, it's cheaper in the other currency. So just think if you were comparing an item in dollars to euros, and you compared several items in dollars to euros. Well, if you found the cheapest item in dollars, it would also be the cheapest item in euros. It's not going to be the cheapest in dollars and the most expensive in euros. That wouldn't make any sense. The cheapest in one is the cheapest in all. The most expensive in one is the most expensive in all. All right. So let's do this. Let's do this. I don't know why it opened that way. It's weird. Nope. We gotta go way past there. Here we go. All right. So getting down to brass tacks. The consumer price index, blah, 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 all the same stuff that we were just talking about. I'm not gonna read it a third time. So this is what I was talking about for CPI values, and I made up some on the spot that were in the ballpark of this for like comparing 1950 and 2020. So 1990, the CPI value is 130.7. In 2005, it's 195.3. These values have the same idea behind them as saying it's $4 to get 5 euros. This is kind of that same idea. But it's not exactly that, because it's not like you're going to get $130.7 converting between these two. This would be converting back to whatever year the CPI was 1. So $1 back in probably like 1990. Why did I say 1990? 1900, because I'm looking at that year, that's why. So like $1 in 1900 would be $130.7 in 1990, and that's if the CPI of 1900 was 1. So again, we're just pretending the CPI in 1900 is 1. That means $1 from 1900 would now be worth $195.3 in 2005. Now, do we really need to think about going back to the $1 in 1900? No, absolutely not. No one does it that way. It's just the idea behind it. And again, you just draw a box, cross multiply, boom, that's all it is. So we have a cost of a movie ticket in 1990, and it was $6.50. Based on my memory, that actually seems a little high, at least in our area. Maybe New York City was that price, but either way, not the point. So they ask us, what would that cost in 2005, assuming that movie tickets went with inflation exactly? So set up a proportion to compute the cost of a movie ticket in 2005, which originally cost $6.50 in 1990. This is not saying that you're going to go to the theater and this is exactly the price that you see. We are taking the price from 1990 and we're turning it into a price from 2005. And then we could actually, in 2005, we got to get our time machine out, go and look at the movie theaters and see if they're above or below that, to see if they overinflated or uninflated. Or deflated. Why is it uninflated? So again, just drawing a box around that. Now remember, please remember, you are not doing this. This is completely wrong because these are labels. I know they look like numbers, they're labels. Don't you dare draw your box that way. They're labels. 1990 literally is just apple, 2005 is just orange. Your box is this. These are literally the only 4 numbers you can even draw a box around if you're drawing the box. So there's 3 numbers in corners and a blank, so that's our x. So we can cross multiply and solve from there. So we're going to go with 130.7 over 195.3 is equal to 6.50 over x. Give me 30 seconds. So we're going to cross multiply. So we get the 130.7 times the x is equal to the 6.5. I'm going to drop the 0 times the 195.3. Then we pull out our calculator, which is right here. Clear. So we're going to do 6.5 times 195.3. We're going to get 1269.45. So 130.7x is equal to 1269.45. Ooh, that got ugly. .45. Then we divide both sides by the number in front of the x. 130.7. And we can just do this divided by 130.7. And we get 9.7. Now we're talking money, so let's go 9.71. Let's round to the nearest penny. Generally with money, we're going to round to the nearest penny unless you're told otherwise. Now remember, the answer is not just $9.71, it's $9.71 because this was a cost of an item. So this would be the price in 2005 only based on inflation. Now again, I'm not saying this is the actual price. This is the price scaled by inflation exactly. Movie theaters could have chosen to charge a little more because they're high demand, they're high entertainment. Entertainment tends to scale more versus necessities. And the one thing I find interesting is that electronics have gone down over time, which says they're necessities. A lot of people years ago wanted to argue that these weren't necessary. The internet isn't necessary. Computers aren't necessary. Yes, they are. In this world, yes, they are. This isn't 1900. Computers are necessary, which is why they've deflated over time. Bacon is not necessary, so it is overinflated. Ribeyes are not necessary, though delicious. So they have overinflated. So you go to the movie theater in 2005 and maybe it was $10 for the ticket, or maybe it was $9 for the ticket, or maybe it was $12 for the ticket. Obviously, prices are going to be different from theater to theater because they have different qualities. Some theaters are fancier, some are kind of run down and ready to be torn down. Back in 2005, I can think of one in Chesapeake that was in that kind of state that is no longer there. All right. Okay, so this problem was a CPI problem. The next problem we're going to do is a currency conversion. Now, we are going to focus in Chapter 3 on conversions. We will be doing problems just like this in Chapter 3, and it's literally going to be the same thing, but we can actually introduce it in Chapter 2 because it's just a proportion. I've already talked about this, in fact, and this was well, I swapped the numbers, in fact. I think I did $4 was 5 euros, but that's not a big deal. Hopefully there's no audio issues across the board. I just got a weird message. I'll try talking a little louder if that's necessary. It could be maybe just need to turn your volume up. I don't know. Let me know if anything happens though. And I know I've said this a couple of times, but if there's ever an issue with the audio live, especially if it's cutting in and out due to, quote, internet instability, which is the message I get, that the recordings are always fine every time I've looked at them. So you can just go back to YouTube to catch that section, because it's usually just a few minutes when that happens. And it's because I'm not the only one Zooming at home right now. So assume the ratio of euros to dollars is 4 euros is $5. So the opposite of what I said last time. Not that it matters. I said we had a stronger dollar. They say we have a weaker dollar. What is more expensive, a mocha latte that costs 2 euros or one that costs $3.50? So some people will say, oh, 350, that's a higher number. Well, no, they're not even the same currency, just in the same way that the movie tickets weren't in the same currency because we were talking about different amounts. Yes, it's still a dollar, but the dollar in one year is different than the dollar in another year, especially if you're looking at a large gap. So we have a 2 euro latte, the 2 euro latte, and then a $3.50 latte. Notice when they create the table, they did not sit them next to each other because that would not be the same currency. This is like the 1990 dollars. This is like the 2005 dollars, but we're not calling them those things. They're euros and dollars. So this is just current year, we could say. This is all 2020. Whether these conversions are the exact ones, please don't take it that way. It's definitely not the case. So the thing that we want to know is, they put the X here, but honestly, I'm gonna write a Y here. Finding either X or Y gives you a way to compare. You can find either X or Y to compare. That's the note I gave earlier. Let me pull it up. Where all you have to do is just read across a row. I even have it currently highlighted. In a CPI table, you just read across a row to compare the prices. So they asked us to find, to convert the they asked us to convert the 2 euro latte to the American dollar. And then we're gonna compare the price converted to the actual US latte. So this is like Starbucks in Europe versus Starbucks in America. In Starbucks in Europe, you're paying 2 euros. Starbucks in America, you're paying $3.50. Where is the more expensive latte? So you could convert the American latte to euros, or you can convert the European latte to dollars. It doesn't matter technically which one you do, but Since they asked for X, we will find X. That is important for the quiz coming up, which we're going to see that question shortly. All right, so you imagine drawing your box, you might try and draw it this way. And this is a bad idea because you have two variables. So that means you can't do that. So that's a bad one. You might try and do it this way. And this is a horrible idea because these are labels. Now, these are actually that is the right number that goes here, but that's not the number that would go here. These are labels. They're not the data. That just says apple, that says orange, essentially. So no, you don't draw your box that way. The numbers are everything in this region. Now, if I drew my box that way, I drew my box this way, we've got number in a corner, number in a corner, number in a corner, and a blank. This is where I had the Y. Now, this would be a way of solving a proportion. You would be finding Y, and you would be able to make the comparison. But again, I want to do exactly as they ask, and we're going to find X. So that means I've got to draw it this way. See, I had to use the CPI values above to find that. These conversions, this 4 and this 5, those are just like CPI values. It's a base in one comparing a base in the other. So that's how we have to draw our box. So that would give us the equation 4 over 5 equals 2 over X. 4 over 5 equals 2 over X. Cross multiply, we'll get 4x is equal to 5 times 2 is 10. I'm not going to write the 5 times 2 because that's pretty easy. You're going to divide both sides by 4 to solve for x. And that tells you that x is equal to 2.5. Now x was right here, and that's in the American dollar. So it's $2.50. That says that the 2 euro, that looks like a cent. Why did I draw a cent? The 2 euro latte costs $2.50 in America. So the 2 euro latte would cost you $2.50 in the USD, not USA, USD. The undo button's killing me right now. Quit scrolling back up. So it's not saying that if you just transported that latte to America, it cost $2.50. The American latte, the one you buy from the American shop, was $3.50. So the 2 euro latte costs $2.50 with American dollars. The one in America costs $3.50. This is less than the $3.50 latte in the USA. So they asked which is more expensive. I'm answering which one's cheaper. But you just flip-flop it and you have the true answer. The one that's more expensive is the American latte. The American latte is more expensive because when you converted the European one to the same style currency, it was $1 less. So America's got that upcharge on the latte. No surprise. All right, I need to annotate and clear. There we go, off of annotate. So, same idea with number 3, and they're even going to keep the same base values of 2 and 3.50, but they're no longer euros and dollars. They're saying we had a $2 Starbucks mocha latte in 1990, which I feel like Starbucks was just starting up then, not that it matters, or a $3.50 Starbucks mocha latte from 2005. So now instead of comparing a latte from Europe versus America, we're comparing lattes in America one year versus another and seeing when was it cheaper to be buying these lattes when you consider all the different things in the world that you'd be buying, which is what CPI accounts for. So is it cheaper for you to be drinking lattes in the past? Well, I guess 2005 is in the present. The way back past of 1990 or the slight past of 2005. So, well, that's a $2 latte in $1990. See, everything's well labeled. $1990, $2005, the price in 1990, the price in 2005. We have the CPI values that you are not memorizing. I do not memorize them. I would look them up on a table. And once again, you could definitely call this blank a y, and then you could compare this one to that one, the 2 to the y. And you could definitely do that by cross multiplying. You would draw your box this way to get your 4 corners, and the blank would be the y. But that's not what I'm going to do. I'm going to find the x, which means I need to draw my box this way. Again, if I'm actually drawing the box. Most people stop drawing the box after practicing this enough. So that's the proportion I'm going to set up. So we're taking the 130.7 over the 195.3 equals 2 over x. Now, remember, the proportion that I set up, I don't have to set it up this way. I could go 130.7 over 2 equals 195.3 over x. I could go 2 over x equals 130 over 195. There's 8, arguably 16 ways to set this up correctly, but there's also ways to set it up incorrectly. I can't go 130.7 over x equals 2 over 195.3, for instance. Cross multiply, you'll get 130.7 times x is equal to 195.3 times 2. Scroll down just a little. Oh no, I didn't hit enter at the beginning of all this. Classic rookie mistake, Beckner. So if I insert a page, it's going to do that. All right, so we're just going to start a fresh one. I'm going to hit enter a million times to make sure that that doesn't happen again. Word is an odd duck. We're going to rewrite our problem. 130.7 over 195.3 equals 2 over x. Cross multiply, you get 130.7x equals, I'm just going to go ahead and, in the interest of time, since you saw it written once at least, multiply 195.3 times the 2, and that's 390.6. Then you're going to divide both sides by, where's my draw? There we go. Divide both sides by 130.7 to give us x equals, divided by 130.7. We get x equals 2.988. So rounded to the nearest penny would be 2.99. Now that was $1. Now this is specifically the dollars in where? We're talking about the dollars in 1990. Currency. When they write things this way, this 1990 and a dollar symbol, that's saying in the currency of 1990, the 1990 dollar. So the X is $2.99. So we just turned the $3.50 latte from 2005. We said, well, what would this cost if we bought it with $1990? It would cost us $2.99. Well, we want to know which one is cheaper this time, right? No, they said which one's more expensive. So which one was more expensive? Well, it's the higher one. So it's the 2005. So again, this X is now $2.99. So the more expensive one is the greater. All you're doing is comparing this number to this number and you're looking for the bigger one. That's it. That's all you're doing. 3.5 is bigger, so that says that the latte costs more in 2005. So that says that Starbucks has increased their price with inflation, but they've also decided to charge a little more on top of that. Now, maybe they're charging more because maybe coffee beans are more expensive. Maybe their employees are more expensive to pay for now. Or maybe they just want a higher profit margin. It could be a combination of all of those things as well. All right, so let's clear our screen. And I just realized that the answer is going to go away. The latte in 2005 is more expensive. There we go. So this brings us to our quiz. Question 4, and that's on page 101. This is your quiz. Answer A and B. The same instructions we're seeing on your whiteboard. Page 101, find the answer to A and B. Round to the nearest whole number. Now, everything before I was rounding to the nearest penny because it made sense to do things that way. We're no longer talking about small dollar amounts. We're actually talking about billions of dollars here. So the penny wouldn't even be seen here. You would just be saying like a 0.3 billion. Just to make this as simple as possible for answer, so I don't get someone writing 195.3 instead of 195.4 and then missing 50 points on the quiz, because I'm not going to give partial credit for rounding on this quiz. You've got to be careful. Round correctly. Round correctly. Pay attention. Check it before you type it in. Don't rush. So all you have to do for this quiz is find the answer that goes here and the answer that goes here. Now you see two tables for this. You've got blah, 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 blah. This table is literally the same thing as the one that's part of question 4. These are exactly the same thing. Do not think you're answering two different bits of information. I also said you do not need to fill in any blanks to actually get this done. You do not need to fill in any blanks to get this done. So you do not need to get the answer here. You do not need to get the answer here. You do not need to get the answer here. And you definitely don't need to get the answer here. Now, yes, you could make the analysis that they ask you to do to determine the year when the receipts are greatest when adjusted for inflation. You could, instead of finding A and B, what some other student could do is find this and this, maybe they call them C and D, and then you could make the analysis to determine when the receipts are the greatest. So remember, you're just trying to complete a row, and wherever the biggest number is, that's when they were the greatest adjusted for inflation. But that's not the question I asked you to do for the quiz. I just want the numbers. I will even tell you the answer to this, not the answers to A and B, the answer to this question. When you find A and B, you should notice that the receipts from 2000 are the greatest when adjusted for inflation. So that's the middle column. So B should be the biggest number out of A, B in this 2154. I've spoiled that for you. So if you get the answers to A and B isn't bigger than A, guess what? You done it wrong. You done goofed. All right. So let me clear the screen again. All you're finding is A and B. Again, for actual analysis, you could have completed the top row or you could have completed the middle row. But I am asking, but I am just asking for you to answer A and B. Yes, again, this is the quiz. So find A and B. How do you do this? The exact same way we did the last 3 questions. It's the exact same thing as finding that theater converted to a new price. It's the exact same as converting the latte from one currency to another. It's the exact same thing as converting the latte from one year to another year. It's just you've got a scary amount of open space and stuff, but you're just trying to figure out how to draw a box where you'd end up with 3 corners that are numbers and 1 that isn't. Obviously, this is not going to get you anything because I've got 1 number in a corner and 3 blanks. So let me show you what one student would like to do probably. They'd like to do this. This is a box that would give you this as an answer. I'm just going to write an X for a generic X. I didn't ask for that. Don't do it. Sure, you can. And again, then you could find this one in a similar manner. But that's not what I'm asking for. I only want A and B.
going to have a couple weird edits here. So the first thing I just want to point out that this is the discussion board question that I mentioned earlier, which is on pages 102 and 103. Now, if you hear me say anything about start with age 35 then 55, that's wrong. I'm going to be trying to cover that. Again, when I made this recently, I wanted to do it this way, and now I want to do it a different way. But yeah, it's going to be a little easier, a little more consistent. So again, with this discussion board, we'll be starting at age 25 for the first 5 students, then going to age 30 for the next 5, then 35 after that. All right. So let's do this.
So the discussion board is going to be due on Monday. Remember, I did originally say that if I gave a discussion board on a Thursday, that they were going to be due on Monday. Multipliers or proportion values, if you wanted to do it the more arduous way, they gives you how much capital, which means how much money in the bank you have across your savings, your checking, your retirement funds, everything, not just one locality of money. So at 25, your capital to income ratio should be 10%. That's what's set. That is what that says. 0.1 is 10%. So capital income 10%. So that what that means is, let's say you made $100,000 a year. That means when you're 25 years old, if you made $100,000 a year at 25, first of all, kudos. Second of all, it means that your capital, the amount of money you have set aside, should be 10% of that, which is $10,000. 10% of 100,000 would be $10,000. If you made $20,000 that year, that means you should have $2,000 set aside in the bank somewhere. Now these numbers get bigger and bigger and bigger and bigger as you get older and older and older, eventually to 12 when you're 65. Now you might be thinking, how am I supposed to have 12 times as much money set aside if I'm only making 1 times that? If I make $100,000 a year, how am I supposed to have $1.2 million set aside? Well, that's because it's not just taking the money you made that year, it's the money you've made for the last 20 or 30 or 40 years of working. So you keep adding to that pile and adding to that pile. And if you've got investments, if you're putting money away into stocks and bonds and you're getting 7% return on average, hopefully, knock on wood, then your money is going to start to explode eventually and really start working for you. And that's the goal. And that's what most Americans miss out on, is putting money away early, and having it just create more money on its own due to investing. All right, so when you're 25, you're supposed to be saving 12% of your income. So 12% of the 100%. So when savings to income, that's the money you're going to put aside that year. So if you made $100,000 a year at 25, that means $12,000 of that you should take and set aside and add to your pile in the bank. So you had $10,000 because of the capital income, and then by the end of the year, you would have set aside another $12,000, bringing you up to 22 by the end of that year. This mortgage to income ratio, this says that your mortgage that you go get could be twice what you make in a year. So if you made $100,000 a year, that means you would in theory be able to afford a $200,000 mortgage. If you made $100,000, that means that you could afford a $200,000 mortgage. I don't necessarily believe the mortgage to income numbers are a little accurate. They're a little low in my opinion, based on the fact that mortgage rates are so insanely low right now. But that will change later, and maybe these become better multipliers. But for the point of the exercise, just go with it. Education to earnings. So this is saying that the amount of money that you have debt for from your schooling or your continued education or anything. So this is 0.75. So when you're 25, that means that you should have, if you made $100,000 a year, that means that you could have $75,000 in school debt and, quote, be okay. And then by 30, you could only have $45,000. And then by 35, it's zero, which means you should pay off all your school debt by the time you're 35. Now, in reality, I know most people can't do that. We're not saying this is absolute end all be all, but this is what we try to mimic. At least that's the idea. All these X's afterwards, that means it's still just zero. You're not going to go back to school and acquire more debt, again, just under a normal circumstance. Stocks and bonds Oh man, I tell you what, in terms of my personal opinion, that is not financial advice. This column is complete trash. I don't think, again, my opinion, I'm more of an aggressive investor because I'm on the younger side, air quote younger, so older than probably most of y'all. Uh, but bonds are a safer investment that I just think you want more when you're in your 40s and your 50s. So in my mid 30s, I literally have 0 pennies in bonds personally, but that's not, again, not financial advice. I'm aggressive because I know I got plenty of time to make up any losses in the long run. But plenty of people are much safer investors than me. And they might go with this, all right, with my investments, the money I'm not using every day, the money that I put away and never touch again until I retire, half should be in stocks, half should be in bonds. And then eventually they say, all right, when you're really old, you want less in stocks and less in bonds. And please don't take that really old as offensive. Really, really old is not 60 or 65. We're all young at heart. Okay. So, point of the exercise, questions 1 through 5.
All right, so I'm coming back in and just going to point this out. Question 1, it says you are 35 years old. Please ignore that if you are students 1 through 10 or 16 and up. Again, the first 5 students are going to come in and answer these for age 25. So student 1 answers number 1 for age 25. Student 2 answers number 2 for age 25. Student 3 answers number 3 for age 25. Student 4, student 5 for age 25. Then student number 6 comes in and they'll answer number 1, but for age 30. Student 7 answers number 2, but for age 30. Student 8 answers number 3, but for age 30. Student 9, student 10, and then student 11 comes in and answers number 1 for 35. Then 12 through 15, you get the idea. Student number 16 answers number 1 for age 40. Student number 21 answers number 1 for age 45. The pattern should be clear with that. So again, you can see the discussion board assignment here. 102 is where the chart was, 103 is where the questions are. You can see there is a 6th question, but this is really only just one specific age. And this is extremely open-ended. There is no accurate answer. So you could just answer number 6 on your own. Don't put it in the discussion board, but just think about that. By the time you were 65, what salary would you anticipate making? That is a difficult question to answer because we don't know what inflation is going to do over the next 10, 20, 30, 40 years. Yes, the Federal Reserve tries to keep it at 2%, but you just never know what's actually going to happen. So hopefully there's no confusion there. I think I've made it clear enough. Let me get to where we should be.
Chapter 3. Definitely won't finish this section today, given that we have about 20 minutes left. But we will definitely start it. And I've already mentioned that really, I've already taught you how to handle half of this chapter, but I'm going to teach you another way that is better. As I always say, I like to teach multiple methods in this course because one method, method A, may be great for problem 10, and then you get to problem 13, and method A kind of sucks or is more difficult at least, but method B would be able to knock it out like that. Now, does that mean you have to learn both methods? No. If you just learn method A, then you can go with method A and you're just going to have a longer problem for that second one. But if you learn both methods and you understand that method A is going to take longer on the second one, you know, to switch to method B, and there you go. Boom. So units and conversions. So units are the things like feet, or miles, or inches, or femtometers. Those are all distances. They don't have to be distances. A unit could be gallons, so talking about a volume of liquid. Or it could be hertz, which would be cycles per second, something we use for waves. So sound, when you talk about a sound wave, it's in hertz. It's one of the different units. And Notice the first ones I said were all distance. I could say 1 mile, or I could say 5,280 feet, or I could say, hold on, give me a minute because I got to calculate it. I don't know it off the top of my head. Or 63,360 inches. So saying 1 mile is the same thing as saying 5,280 feet, is the same thing as saying 63,360 inches. Those are all literally the exact same thing, but with different units. So units are also like dollars versus euros, or $1995 versus $2020. Those are all units. Now, in quantitative reasoning, it is extremely important to use your words, to use your units. That's why if you say, how far is it to the store? I'm going to erase this in a second. How far is it to the store? If you say 3, if that's your answer, that is terrible. 3 is not how far it is to the store. You're probably meant to say 3 miles, but maybe you meant 3 kilometers, or maybe you meant 3 nautical miles because you live on an island offshore of North Carolina or something like that. I don't know. But you have got to use your words. What's the temperature outside? Oh, it's 68 degrees. Wrong. It is not 68 degrees outside. It's 68 degrees Fahrenheit outside. Even just saying degrees isn't enough technically. Oh, how much liquid do you have in your cup? Oh, I have 8. No, you don't have 8. Oh, okay, I meant to say I have 8 ounces. Actually, no, you don't have 8 ounces. You have 8 fluid ounces in your cup. An ounce is technically different from a fluid ounce. I'm generalizing here, pretty much the only liquid out there that 8 ounces would be 8 fluid ounces is water, because its density is 1. We'll get into densities later, but we won't get too deep into them, pun intended. But if you had 8 ounces of syrup, that's probably like, I don't know, 7 fluid ounces, because ounces is a weight, fluid ounces is a measure of volume, and syrup is more viscous than water. Viscous means thicker, thick with 2 C's, and because it's syrup, and not the sugar-free kind, that nice, thick, straight from the tree in a barrel, whatever. Now I want pancakes. Okay, so those are your units. What's the whole point of this? Unit conversions. How do we go from miles to feet? And I erased the feet part on accident. How do we go from fluid ounces to another type of liquid measurement, volume measurement? How do we go from grams to tons? How do we go from miles to kilometers, if I didn't say that? Feet to inches, anything like that. Going between the standard US system, going between the US and the metric system, it's all the same. You can set them up as a proportion if you like, and you cross multiply to solve as long as 3 of the 4 spots are numbers, the same exact thing we've been doing. Now, how do you know how to set this up? You use your words. You would write miles over feet to start this, and then you put the numbers that you know the conversion factors for in one of them, and then the thing you know one of but not the other on the other side. Cross multiply solve. That's it. Or capitalized or, the thing that we'll be focusing heavily on, because we've already done we've already done proportions over and over and over and over and over, you can use dimensional analysis. So the 2 methods of conversions are proportions or dimensional analysis. Proportions are great when you're just converting from one thing to another where you know exactly the conversion factor from one thing to another. So if I want to go from miles to feet, doing a proportion is not bad because I know exactly how many miles is exactly how many feet. But if I wanted to go from, say, feet to kilometers, that's not a very common number to see in just a general table. Sure, you can Google it, but that's not the point. In the table that we would provide for you in your homework or in your textbook, you would probably have feet to miles somewhere, and then you'd have miles to kilometers somewhere. So that would require 2 conversions, which is a little bit more of a pain in the butt because you would have to set up 2 proportions. You'd have to do a proportion going from feet to miles, and then another proportion once you had that answer going from miles to kilometers. So that gets annoying. Dimensional analysis, instead of doing a proportion to then do another proportion, is just multiply by something and then multiply by something. It's a lot less work, it's a lot less time, it's a lot less effort, but so many people just want to say bad things about dimensional analysis Because they don't know what to multiply by. How do I know which thing goes in the top and which thing goes in the bottom? How do I know anything at all? Out with the old, in with the new. That's the whole thing. It's out with the old, in with the new. Out with the old, in with the new. That's dimensional analysis. That's all I would have to say in theory, but of course we'll say more. So it's a way of converting from one unit or rate into another unit or rate. Rates are just types of units, but they're fractions. So the main idea behind dimensional analysis is that you multiply your original value with the units in the proper spots as a fraction. So what I mean is, if I was converting miles to feet, if I had 3 miles, I write 3 miles. I do not just write 3. I do not just write 3. I do not just write 3. So I am going to highlight that because it's important. With the units in the proper spots as a fraction. So write the original number with its units, 3 miles, or whatever it might be. So you're going to multiply by a fraction whose numerator and denominator are the two values in a conversion factor. There are a very small amount of conversion factors I ask you to memorize, and they all have to do with time. I will not ask you to memorize any feet to miles or centimeters to inches, none of that stuff. Gallons to ounces, or fluid ounces, excuse me, I almost said that incorrectly. You don't have to memorize any of those. You would be given you're given charts in your homework problems. You could pull up your textbook for most of them as well. And if I give you a test, I'll give you the couple of conversion factors that you would need as like a formula sheet, if you will. Now, I say formula sheet, but that's literally all it'll be on your formula sheet. All the formulas we've taught you for the past 5 or so weeks, they're not on it. It's just conversion factors. So you multiply by a fraction where the numerator and the denominator are the two values in a conversion factor. What I'm saying is if you wanted to convert between miles and feet, you'd be multiplying top and bottom with these numbers. The top might be the 1 mile, or the bottom might be the 1 mile. Top might be the 5280 feet, or the bottom might be the 5280 feet. So how do you tell which one goes top and which one goes bottom? You must make sure that in the conversion factor, your old units are opposite their original placement so that they cancel. Also going to highlight that. Your old units need to be opposite their original placement so they cancel. By opposite, I mean if your feet were originally in the top, in your multiplier, put it in the bottom so they cancel. If your feet were originally in the bottom, then in the multiplier, put it in the top so they cancel. I don't even write any numbers at first when I figure out my multiplier. This is the first thing I do. I say, all right, what's my old unit? Feet. Where is it? In the top. So in the multiplier, feet have to go in the bottom so they cancel, and I'll be left with my new units. So before we get to this example, I said that I will not make you memorize most conversion factors. The only ones that I do ask you to memorize are time. All caps. You must memorize all time conversions. Specifically, the fact that 60 seconds is a minute, 60 minutes is an hour, 24 hours is a day. Let me hit enter on that one just so it doesn't look wacky. And then 365 days is 1 year. Yes, it's 365.24 something because of leap years, and even leap years aren't exact. We do not have leap years every 4 years. There are years we skip leap years. We have a leap year. I think 3000, there'll be that leap year gets skipped, and there's some others like 3200 maybe. Don't worry about that. There are 365 days in a year for our intents and purposes. Please notice there's no days to months conversion. Yes, there's also 12 months is a year, but I don't want to type that because you might think that, oh, well, I can go from days to months and then months to year, and you can't. Because how many days are in a month? Well, January's got 31, February's got 28 or 29, March has got 31, April's got 30, et cetera, et cetera, et cetera. So there's no consistent answer. So we should not be using the days in a month to convert to months because there's absolutely no consistency. So these are the ones that you'd have to memorize. And I guarantee you'll see one on the midterm. Now, I might just ask you to go from days to years. I may ask you to go from seconds to years. You could need one or multiple of these proportions or dimensional analysis setups. So we will, of course, go through all of those different types. Okay. Yeah, anyone who's got a birthday on February 29th, you're probably like 7 years old, I guess, if you're 28, right? That's the way you'll like to think, especially when you're in your 60s, I guess. That'll be the fun way. All right, so getting down to this. So this is a conversion factor. 1 mile is 5,280 feet. That's what we mean by a conversion factor. And I want to actually show the work process. So that was the typed up work if you saw it, but let's do this by hand. Let's say I said, all right, you went 0.75 miles. Maybe the distance from your house to the store, the grocery store, is 0.75 miles because you're right around the corner practically. And I go, well, how many feet would that be? So to convert 0.75 miles to feet, sure, you could do it as a proportion. I'm not going to show you that because, well, I will, but let's do it this way first. You start with your highlighter. You start with your 0.75 feet, 0.75 miles, excuse me. So this is our original value. That's what we start with. The process is you start with your original value with its units in the proper spot. So there's our original value. And then we're going to multiply. We multiply by a fraction. That's dimensional analysis. What do you do with your number in units? Multiply by a fraction. What do you do with your number in units? Multiply by a fraction. Now, I'm not even going to look at this at all for the first second. Doesn't matter. I know that I want to go from miles to feet. I'm currently in miles. I need to get rid of them. These miles count as being in a top. See, that's in a top. If the miles were in a bottom, they'd be written something like that. There would have been a per in front of the miles, which can certainly happen. So because the miles are in the top and I want them gone, whatever number I'm going to have in the bottom, I know I have to put the miles in the bottom, so that way they will ultimately do this. They will cancel. They will go away. So I know I want the miles in the bottom. Now I can look at the conversion factor. See, I didn't even look at that at all to know miles go in the bottom. That's automatic. All right, well, the conversion factor says that 1 mile, ignore the plural s, that's okay, is 5,280 feet. So where do I put the 5,280 feet? Exactly in the place that's left. There's nothing to think about. That's it. That is dimensional analysis, and everybody makes it 1,000 times more complicated than it actually is. Miles top, miles bottom, units cancel just like variables and numbers. So you just multiply 0.75 times 5,280. We can use a calculator for that. Now, before I hit enter, instead of asking, does it make sense when I get the answer, I want to predicate this and say, what type of answer do you expect? Do you expect this answer to be 10 million, 10,000, 5? Well, this is less than 1 mile, and a mile is about 5,000 feet. So if we have a number that's less than a mile, the answer should be less than 5,280 feet. Probably not too close to 0 because it's almost a mile. But let's see what happens when we hit enter. We get 3960, and I would say that answer makes sense. Now, if you do this in a quantitative reasoning sense, it says wrong, 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 no points awarded. It's not 3960, and yeah, that's usually what you're just typing in MyMathLab, but again, the point is, outside of MyMathLab, writing pencil, paper, talking, units are important. 3960 what? 3960 apples, 3960 Bob Doles, 3960 feet. That would be the equivalency to 0.75 miles. And it does make sense. So I just have the same thing typed up here, as you can see. The miles cancel. Same way, and we get the answer. We see feet left, so that's it. Now, what I'll do real quickly, I'm just going to show up here the proportion way. How would you have done this? Well, you have to use your words first because you're going to ultimately set a fraction equal to a fraction. That's what we're going to be doing. But before I throw anything anywhere, use your words. What are the things we're converting between? Miles and feet. Which way do you want to do it? I'm going to go miles on top and then feet on bottom. That's my choice. Please, for the love of math, understand the abbreviation of miles is not M, it's MI. You will get answers wrong in your homework if you don't know that abbreviation. Maybe even a test ultimately. All right, so miles to feet. All right, well, use the conversion factor as one of the sides of the fraction. 1 mile is 5280 feet. Now, when we do proportions, we don't write the units. You can, but it's going to get ugly if you do. So 1 mile, I was saying that, so I had to write it. 1 is 5280. The reason with proportions that we don't have to write the units is because we're staring at the units right here by knowing what they are. Anything from the top is a miles, anything from the bottom is a feet. Then in our problem, we were supposed to be converting 0.75 miles. So where does the 0.75 go? Well, where the miles are, top. There's a 0.75, which makes that an x. You will cross multiply to get x equals 0.75 times 5280, which is literally the same thing we just did. It's 3960. Because x was in the bottom, we know it's feet. Now again, you might be saying, I love proportions. That way seems so much simpler. Why would I ever want to learn something new? Because learning new things expands your mind, and also these are not always that simple. If I asked you to go from feet to kilometers, for instance, you'd have to go from feet to miles, then miles to kilometers. Because most unit conversion tables can only give you so many things. Again, the internet can give you everything, but that's not the way the homework and tests and maybe even a quiz question at some point are designed. I say maybe, but honestly, it's definitely. We will have a quiz involving this at some point. Okay, so that was the way to do it as a proportion, still right answer. How can we tell that it's wrong? So let's say we did the dimensional analysis, and I'm going to keep this in red for the entirety. We have our 0.75 miles. I'll use orange, actually, for the multiplier. Orange is close to red. So everything I'm writing is wrong from here on out. So we take our 0.75 miles, and we know we got to multiply by a fraction. We're doing the dimensional analysis way again. So we're multiplying by a fraction, where it's supposed to be out with the old and with the new, but I'm not paying attention to Mr. Beckner. I'm not practicing. I just want to multiply and get this done. So I know, all right, we're going to use this. 1 mile is 5280 feet. Well, 1 mile is 5280 feet. There we go. We're rushing. All right, so what do we get? The 0.75 is in the top. The 5280 is in the bottom. So you're not going to multiply those two numbers. You're going to have to divide them. So we're going to end up taking 0.75 divided by 5280. And the number we get, wow, our calculator didn't even give us something that makes sense, because this is in scientific notation. The e minus 4, what that says is take this decimal and move it left 4 times. So what that ends up being is, that's a 142. 0.00142. If you fix that number, this is what it is. The 0.75 divided by the 5280. I already think this doesn't make sense because we had 0.75 miles. We're converting this to feet, and 3/4 of a mile is 0.0001 feet. That's not even close to an inch. That is terribly wrong already. But here's another way we can tell that it's wrong. Let's actually pay attention to the units. Now, in the proper way, we had miles in the top and miles in the bottom. Anything top and bottom cancel. That's not the case here. These miles are both in the top. When you have 5 times 5, yes, it's 25, but think in exponents, it's 5 squared. When you have 7 times 7, it's 7 squared. When you have x times x, it's x squared. Units work exactly the same way. So miles times miles is miles squared. The feet unit is still in the bottom. So 0.75 miles is equivalent to 0.000142 miles square per foot. That makes, not mo, that makes absolutely no sense. It's got to be wrong. Not only is the number terrible because it's way too small when you think about it, the units are complete trash. They make no sense. I don't even know what a mile square per foot is. So if you do, please email me and tell me. Take your time, pay attention, use your units. If you don't write units along the way, you will make mistakes. Guess what? I've tried to do it that way at times. And I'm pretty good. I'll get them right, usually. but I definitely make way more mistakes when I'm rushing and I don't want to write my units and show the canceling and all that stuff. It is critical. All right, so that's all the time we have for today. So this was just a, we'll say, light introduction to this. When we come back, we'll do more of these. We'll also show you what happens when you have to do that middleman conversion, like I was kind of saying, the feet to miles to kilometers, where it would be two proportions or it would be just two multipliers. But again, go ahead and practice these simple ones. Maybe try converting 2 feet to inches because 1 foot is 12 inches. You should be able to do that pretty quickly. And then maybe something like, I don't know, since you've done one like this, maybe go with 3 miles to feet. That would be a good one. All right.
So just closing out the day, reminding us of our due dates, 2.3 and 2.4, the 16th and the 23rd. 2.1, Excel file currency on the 21st, the discussion board we talked about on the 23rd, and the quiz we talked about on the 23rd. Please do not forget any of your assignments. Remember that this discussion board will count as 2 zeros if you miss it. So please, please, please do not forget this one. This one is going to be critical. Besides that, have a good weekend. Work hard, study hard, and we'll see you on Monday the 21st. Yeah, take care, everybody.